Hello, everyone, and thank you all for coming. My name is Leila. I work at Shopify as a site reliability engineer. I'm part of the resiliency organization at Shopify, whose responsibility is to ensure Shopify is always up and running, ready and reliable for merchants and our buyers across the globe. My talk today will be about a project where we improved Elasticsearch indexing performance as well as the reliability of our infrastructure by using dedicated node pools that are automatically scaled by KEDA scalers. In the next 30 minutes, we will learn how at Shopify we host the search infrastructure on top of Kubernetes. We'll talk about the entire data pipeline that writes data from SQL to Elasticsearch through Kafka and the resilience of its architecture. I will follow by presenting the problem we needed to solve, and we'll share our solution for it, followed by some technical details on how to use KEDA scalers for scaling Kubernetes workloads. And I will conclude the presentation with a Q&A. Shopify is the all-in-one commerce platform to start, run, and grow a business. It is the leading global commerce company that provides essential internet infrastructure for commerce, as well as trusted tools to start, scale, and run a retail business of any size. Currently, we have over 3 million businesses using our platform. We have merchants like Gymshark and Fashion Nova selling their products with us. We represent over 175 countries and have about 10% of the total US commerce. In the summer of 2024, we reached $1 trillion in gross merchandise volume. One of the largest events in commerce is the Black Friday Cyber Monday week, which we call it BFCM. To share more stats about the scale of Shopify, during the BFCM of 2024, Shopify processed around 58 petabytes of data, served more than 1 trillion edge requests, as well as more than 10 trillion database queries, which led to around $12 billion of global sales. Search is a fundamental part of any commerce platform that allows buyers to search and filter for products, or for merchants to fulfill their orders, manage their customers and inventory. And when you go to any online store and search for a product, your request goes to a search engine that is backed by a secondary data store, which is different from traditional databases. And the search engine that we use at Shopify is Elasticsearch. A quick refresher on Elasticsearch: it is a distributed text search and analytics engine. It is built on top of Lucene that has full text search capabilities that are well suited to the e-commerce domain. It's also a scalable and fault-tolerant system, and it handles a lot of the hard parts of running a distributed system very well for us. Elasticsearch stores data that share similar characteristics in a logical namespace called an index. These indices are split into multiple shards, which can be either primary shards or replica shards. We run our fleet of Elasticsearch clusters on managed Kubernetes clusters, GK on top of GCP, and we deploy and maintain them using a custom Kubernetes controller that we have built. Shopify is a large, complex technical ecosystem that is made up of a variety of apps and services. And the biggest service at Shopify is called the Shopify Core, which is a big Rails monolith that powers all of our merchant shops and storefronts. We run Shopify in GCP regions for resiliency. What you're looking at here is a high-level structure of Shopify Core in a single region. The entire Shopify Core in a region is broken down into above 100 logical groups of SQL databases and instances of other services which are simplified in this slide. All of these services power all of our online store functionality for the shops running in that region. In every region, we run one instance of Elasticsearch for Shopify Core that provides search functionality for the shops in that region. To give more context, Elasticsearch is used as a secondary data store. It is utilized to provide additional functionalities such as fast search capabilities, aggregations, or full text search on top of the existing data in the primary data store, which is SQL in our case. We have an ingest pipeline in each region that consists of Kafka topics and Kafka consumers. We produce updates made to records for all related SQL instances in the region to our Kafka topics, and our consumers pick up those messages from the topics and write them to the correct Elasticsearch index in real time. Indexing is a term we will use a lot in this talk. It is the act of writing documents from the primary data store to Elasticsearch. We store Elasticsearch documents in Elasticsearch indices. For example, we have an index that allows merchants to search and filter through the orders they receive, or another index that allows them to search through their products or their customers. Merchants or buyers are able to search these indices, and their queries are sent to the correct Elasticsearch index through a routing layer. Our focus in this talk will be on the indexing path shown here, which we call the indexing pipeline. In the previous slide, we saw the indexing pipeline that brought data from SQL as the primary data store to Elasticsearch through Kafka, but that was really simplified, and we have actually built two different indexing pipelines for two different write profiles. One of them is called the real-time pipeline, which, for example, indexes a product to Elasticsearch and makes it available for search for buyers when a merchant, for example, adds a new product to their online store. The other one is called the reindex pipeline. We have a lot of developers at Shopify. They create indices, modify index analyzers, and add or remove versions of the index. They add or remove fields from the indices, and basically they change the shape of the indices a lot. And when that happens, we need to migrate all that data to a new version of the index and promote that index to make the new feature available to the merchants as well as the buyers. We call this reindexing, which basically means rebuilding an entire Elasticsearch index from SQL records. And as I just mentioned, we have two separate indexing pipelines for real-time and reindex writes, which we see on this slide. As a bit of a background, Kafka is a distributed publish-subscribe messaging system. Data is written to Kafka topics by producers and consumed from those topics by consumers. We have separate Kafka topics for each pipeline. The real-time Kafka consumers consume from the real-time Kafka topics and write to the production indices. These indices provide search results for buyers and merchants. The reindex consumers, on the other hand, do not write to production indices. They only write to indices whose aliases end with a .new. The .new indices get created when we start a reindex for a specific index, for example, for the orders index. The orders.new index will eventually be a copy of the production index for orders, but with different fields and different features. A .new index does not receive production queries because its data is incomplete until all the necessary records from SQL have been written to it. After the .new index is created, some jobs get spawned and read the necessary records from SQL, produce them to the reindex Kafka topic, which will be consumed by the reindex consumers and will eventually be written to the .new index. And to make sure that the .new index also receives the real-time updates, the reindex topic also receives real-time updates made to SQL. After a while, all records in SQL will get processed and no more reindex writes will be produced to the reindex Kafka topic. At this time, the reindex is finished and we can flip the .new index live. Flipping it live basically means changing the alias for the production and the .new index. And after this, the .new will become our new production index and will have the updated fields and features and will be queried by the clients. As mentioned before, our Elasticsearch clusters run on Kubernetes on top of GCP across different regions and availability zones. It's good to know that today the entire Shopify ecosystem, including the Shopify core, its storefronts and other services run across the globe, from North America to Europe and to Singapore. We have Elasticsearch clusters spread across these regions, giving us resilience and availability through redundancy. So let's talk more about resilience, taking a closer look at an example GCP region where Shopify core and its Elasticsearch cluster runs. We have the indexing pipeline updating Elasticsearch when changes are made to SQL records. And we can see here that search queries are sent to the Elasticsearch through a routing layer, meaning that queries made to shops in a certain region are routed to the Elasticsearch in the same region. We know that the first step towards high availability is redundancy, and to mitigate regional failures, we should replicate our systems to another region. The active SQL instances and Kafka topics in different regions, they hold different data sets, and we need to replicate their data between regions so both Elasticsearch clusters have the same data set. And with this inter-region data replication, if one of the Elasticsearch clusters goes down, we can fail over the query traffic to the Elasticsearch cluster that is functional until the other one has recovered. At the application layer, Elasticsearch also provides fault tolerance by being zone aware, meaning that if we deploy our Kubernetes cluster across 3 different availability zones, when Elasticsearch distributes primary and replica shards, it distributes them across these zones in a way that the primary and replica for one shard do not end up in the same availability zone. We use node affinity rules to ensure that 2 pods from the same Elasticsearch cluster do not get scheduled on the same node. And we also taint the GKE nodes so only the Elasticsearch pods are deployed on them. The Elasticsearch pods are given the right toleration so they can be scheduled on the right GKE nodes. With this zone-aware setting, we can also do maintenance more quickly, as we can bring down an entire availability zone for maintenance without being worried about data loss. To give a sense of the scale of search at Shopify, as of today, the search platform team manages above 100 distinct Elasticsearch clusters, some of which are as large as 260 node clusters, and many are as small as just 3 node clusters. And together they store more than 3 petabytes of data. For Shopify core Elasticsearch, the real-time indexing rate can peak at 90,000 documents per second, while our reindex indexing rate peaks at 500,000 documents per second. And as you can see, the reindex pipeline throughput is a lot higher than that of the real-time pipeline. And to recall, reindexes are done occasionally to change the shape of an index. In other words, they are an occasional burst of writes to Elasticsearch. This is actually a nice segue to the problem statement, which will be followed by the solution. What you see in this slide is the distribution of Elasticsearch pods across many VMs running on GCP. As mentioned before, an Elasticsearch index is split into many shards, and each shard has a replica. For example, the production index for orders is split into 1,024 primary shards, each of them having a replica shard, which is shown by a different color in here. This index receives real-time writes as well as production queries. When a reindex starts for maintenance, another index called the orders.new with the same number of shards is created on the same VMs, which will receive the heavy reindex writes. And since the production and the .new index share the same compute and storage resources, the heavy reindex writes will impact the real-time writes and slow them down. And delayed real-time indexing results in stale or inaccurate search results, which could result in lost revenue for our merchants, which is a big deal. So the fact that real-time and reindex writes share the same compute and storage resources leads to reindexes impacting production writes and queries, which leads to pager fatigue because the on-call would get paged for real-time indexing delay, which can only be mitigated by stopping the reindex, starting it all over again, which also slows down feature rollouts for our developers. Our initial approach to solve this problem was to over-provision the cluster to always be ready to handle the load of the reindexes. And this became too expensive as Shopify kept growing and the cost was no longer acceptable. Therefore, we decided to separate the infrastructure for real-time and reindex writes. This was a huge undertaking because it required us to make some fundamental changes to our existing reindex pipeline. The first step to do this was to create a separate GKE node pool just for running reindexes. We leveraged Kubernetes taints and tolerations to ensure that Elasticsearch pods for reindexes only get scheduled on the reindex GKE nodes. Same as for the Elasticsearch pods for real-time writes. Just as a quick refresher, a Kubernetes taint is a mechanism that allows a node to repel a set of pods. Taints are applied to nodes, and they work together with tolerations, which are applied to pods. The primary purpose of using taints is to ensure that certain pods are not scheduled on the wrong nodes. So giving the reindex and real-time toleration to pods will ensure they get scheduled on different node pools, which will provide the first step towards isolation of reindex and real-time writes. We use the Elasticsearch built-in shard allocation settings to force all indices to be hosted on the Elasticsearch pods that run on the real-time node pool, except for the ones whose aliases end with a .new, which should be hosted on the Elasticsearch pods that run on the reindex node pool. Once the reindex is done, we switch the alias for the .new index, which will force its shards to be relocated to the real-time node pool and become searchable by clients. And this way, reindexes no longer impact production reads and writes. Also, since the real-time node pool no longer has to provide for the heavy reindex writes, there is no need to over-provision that node pool, and it gives us a great opportunity to save infrastructure costs. But as you see, now it's the reindex node pool that is burning money. And this is where node autoscaling will come in handy. Ideally, we would need a very small GKE node pool that gets scaled up when the reindex starts. And we expect that the node pool scales up depending on the size, the number of shards of the index that we want to backfill. We picked KEDA, which stands for Kubernetes Event Driven Autoscaling, which is an open source project that provides autoscaling for Kubernetes workloads. It's designed to extend the capabilities of the Kubernetes horizontal pod autoscaler by allowing workloads to scale based on metrics from various event sources rather than just CPU or memory utilization. This makes KEDA particularly useful for applications that need to scale in response to events like queue length, number of incoming messages, or in our case, to automatically scale up the Kubernetes workload when a reindex starts. Scaling up the Kubernetes workload will force the GKE node pool hosting the reindex pods to be expanded as well. KEDA is implemented as a Kubernetes operator, which uses custom resources to define how scaling should behave, and it consists of two main components. One is the KEDA controller that watches for a KEDA custom resource called the scaled object and manages the life cycle of the corresponding HPA resources. The other one is the metrics adapter that collects and provides metrics to the Kubernetes HPA, which then makes decisions about scaling the application pods up or down based on those metrics. KEDA supports a variety of event sources called descalers, and Prometheus is one of them. Each event source is represented as a trigger in the KEDA configuration. Scaled objects are custom resources used for scaling deployments, stateful sets, or any other scalable Kubernetes workload. We define the triggers and scaling behaviors used by KEDA to scale workloads. You see an example of a scaled object on the slide. For our specific use case, we set the scale target to our reindex stateful set that runs the Elasticsearch pods that are used for reindexes. And we also have settings for min and max replica counts. These settings determine the minimum and maximum number of replicas that the stateful set can scale to based on the events that are triggering the scaling action. For us, we set the minimum as low as 3 and the maximum to around 200 replicas. The Prometheus trigger in KEDA enables autoscaling based on the results of the Prometheus query. When you configure a scaled object with a Prometheus trigger, KEDA will periodically send queries to a specified Prometheus server, and the responses to these queries are then used to make decisions about scaling the Kubernetes workloads up or down. And for our use case, we wrote a Prometheus query that calculates the number of shards divided by the number of nodes. And we set the threshold to 1, which means that ideally for peak performance, we want to have 1 shard on a single node. However, if the index has like 2,000 shards and the max replica count is set to 200, we will end up with only 200 nodes, which means that each node will have 10 shards. The following slides show an example for node autoscaling. We have a real-time node pool hosting shards for production indices. We also have a reindex node pool with a minimum of 3 nodes that initially host no indices. So the Prometheus query for KEDA that calculates the number of shards divided by the number of nodes will return 0. KEDA compares the query results to the threshold we have set, which is 1, and decides to do nothing because the reindex workload already has 3 replicas, which is the minimum allowed. Next, the reindex starts for an index that has, for example, 4 primary shards and 4 replica shards, so 8 shards in total. Because of the routing allocations that we have set for Elasticsearch, the shards of the .new index will be created on the pods running on the reindex node pool. Once this happens, the Prometheus query would return a value higher than our threshold of 1, which signals to KEDA to scale the reindex workload up until the result for the query becomes equal to the threshold. Scaling up the reindex workload expands the underlying GKE node pool. Once the node pool gets scaled up, Elasticsearch automatically balances shards across the nodes, so each node of the node pool will have 1 shard. Now the Prometheus query returns 1, which is equal to the threshold, and KEDA will take no scaling actions. After the reindex is done, and we switch the .new index live, all shards from the reindex node pools get evacuated by Elasticsearch and will get scheduled on the real-time node pool. At this point, the Prometheus query returns 0, which is below the threshold, and consequently, KEDA decides to scale down the reindex workload. The reindex workload gets scaled down by KEDA, which consequently scales down the underlying GKE node pool to the minimum number of nodes, which in our case was 3. And KEDA will take no further actions until a new reindex is started. With dedicated reindex nodes, we were able to reindex our orders index, which has around 100 terabytes of data, 40% faster. The queued byte threads on the real-time nodes was also dropped by 98% during reindexes, which helped improve real-time writes performance. And as a result, the pager fatigue due to this problem was no longer an issue, and developers were able to ship features faster. Leveraging node autoscaling, we were able to reduce the total number of CPU cores and memory used by our real-time node pool by 58% and 15% respectively, which led to a total saving of 43% in infrastructure costs. This was only an example of the interesting problems we solve at Shopify. We're always looking for people who are interested in solving problems at scale. Scan this QR code to get more information. And if you have any questions, I'd be happy to answer them. Thank you. Oh, we have one question.
Yeah, it's going to be a quick one. When you scaling down your re-indexing node pool, how do you make sure that you accidentally don't shut down the node that still has a shard that didn't get moved to the other?
That's a really good question. Well, we are saved by the results of the Prometheus query. If we have data on the nodes that we want to scale down, the query will not return 0. It will show that there are some shards on those nodes. So that query that divides the number of shards by the nodes will not return 0.
But at some point, some shards will move and some...
The node pool gets scaled down when all shards have moved. Only when there are 0 shards on the reindex nodes.
Good. Thank you.
Thank you.
Hi, one more question.
Sure.
How fast do you scale up the worker nodes? Because when you create the index with 1,000 shards, it means that do you scale up all the worker nodes at once?
It's you are able to define the scaling behavior in the scaled object config. You can, say, scale up for me 5 pod which means 5 nodes at a time, or by a percentage, if I'm not wrong. In our case, for the one that you mentioned, a very large index, I believe it took I think 30 minutes to scale up, which we are okay with because this is a maintenance kind of thing. So like 30 minutes is basically nothing. It's just system warming up.
Thank you.
Thank you.
Hi. I didn't really get how you manage the affinity between the shards and the nodes they are hosted on. Is that an Elasticsearch feature or your custom controller?
Great question. Yes, it is. It is the Elasticsearch feature. You are able to define some custom node attributes, and you are able to say that if this index has this kind of alias, always like allocated to a node that has this naming pattern. So this is a feature that Elasticsearch provides, and the shards of that index follow the rule and will end up getting hosted or like scheduled on our case on the reindex node pool.
Thank you very much.
Thank you.
Hi, thanks for the brilliant talk.
Thank you.
What kind of ballpark figures do you have for when data has to move around after you've completed the reindex?
I didn't catch the beginning of your question.
Oh, what kind of ballpark figures in terms of time does it take for the data to move around, when you've done a reindex?
When we are done with the reindex?
Yeah, and you're scaling down things.
Yes, great question. Obviously, it depends on the index that we're running, but for our largest, I think it took about 2 hours, like to be fully, for all the shards to fully move from the reindex nodes to the real-time nodes.
Okay, cool. And that's orders of terabytes, like hundreds of terabytes, you said?
Yeah, yes.
Thanks.
Yeah, thank you. Thank you, everyone.